is there life out there on other planets? So the reason for asking this question, is there life on this planet that you've never heard of? It was discovered in recent times. It wasn't discovered yesterday, but there was a recent study published saying that, well, maybe there's life there. And then talking about, well, why do we think there's life there? And so this is a reasonable time to talk about that. What is it? Well, it's an exoplanet, meaning something outside of our solar system, but it has been identified as a planet around another star. And it's 120 light years away, so it's not exactly close, but it's not anywhere near as far as some things would be. It's in the constellation Leo, orbiting, as you might guess, a star called K2-18. The B indicates the second planet out. It's quite a bit bigger than Earth. The radius is only about 2 2/3 that of Earth, but the mass is quite a bit more. Now, it is considered to be in the habitable zone, meaning a zone where liquid water can exist. Now, that's not to say that life couldn't exist in other forms, but that's obviously a place to look if we're looking for any kind of life. We know it works with water, so why not at least look for that? So that counts. And I put the word probably there because there is some dispute as to whether this particular planet actually is in the habitable zone. It kind of depends on some assumptions. The criteria that they're using assumes a rocky planet with some oceans, and it's looking like this is probably a full ocean planet that is completely covered in water. May or may not completely apply. So they're not completely sure about that. But anyway, because of the James Webb Space Telescope, there are some studies that have come out quite recently talking about it and saying this is probably the most likely time we might have discovered life, potentially. As I said, it's considered as probably an ocean planet, meaning completely covered in water, and that's why it's drawn that way. It's orbiting a red dwarf. That's shown in this picture here. On the left-hand side, you can see the star being colored kind of red.
Do we have any idea how old the red dwarf is?
The question was, do we have any idea how old that is? The answer is, I don't know.
Red dwarf stars tend to be more settled and calmer. When they're younger, they tend to have frequent periodic flares that would strip away the atmosphere and probably the water around the planet at that distance in the habitable zone. If it's an older red dwarf, then it may have settled down into the sedentary phase of its lifespan, and therefore, and that can last several billions of years.
This brings the question up, how can we detect life outside of Earth? I mean, we're saying, hey, it might be there. Well, how do we know that, or how do we at least think it's possible? Well, one way to find out is just to see it. Now, obviously, we can't do too much of that yet. Now, in the solar system, we probably would have noticed it on the moon, maybe on Mars. When we get there, maybe if we drill through the moons in Enceladus and Europa, there's subsurface oceans. If we see some seaweed or squids or something, we'll know it's there. But we're almost to the point where we can do a little bit of that, but that doesn't help at all for everything else that's far away. So you have to do indirect inference in this case, mainly by looking at chemical compositions, which you can infer from various data, and I'll talk about that in a minute. So that's just finding life. I mean, it could just be as simple as an algae kind of equivalent, or something not even depending on photosynthesis. Like we have on Earth, the things around the subsea vents, they're based on chemistry that has nothing to do with the sun. So any of that stuff is possible. Now, there is a separate question about intelligent life. And there you're looking for signal transmissions, or maybe evidence of structures, or some signatures of material or energy use. So for instance, if they have a lot of stuff in their atmosphere like Earth does that isn't really very natural as a result of industrial processes, that could be a tip-off that there's something going on there. So those are ways we might find out about it. Now let's take a little bit more time talking about the atmospheric chemical composition case, because that's pretty much all we really have. What are you looking for? You're looking for reactive chemicals that are really outside of any possible chemical equilibrium. So for instance, oxygen in Earth's atmosphere is always one of the first things people talk about. And oxygen is quite reactive. And so it's not likely to just hang around in the atmosphere forever. Sooner or later, it's going to react with other stuff, and its composition would go down, unless there's something else driving it, such as life. In our case, with photosynthesis, we're constantly generating new oxygen. So that oxygen is being replenished. Now, there always can be individual events that for one reason or another create some kind of storm or explosion or whatever. Something could happen and where you get some chemical that doesn't last very long. And what you're looking for are things that last, like oxygen in this case. It's renewed by photosynthesis. Now, there's a related way of guessing, And that is, look for chemicals that, as far as we know, could only be produced by life. That is, we don't know of any chemistry that could occur naturally that would make that happen. And the example there is Venus. Now, phosphine maybe has been detected on that, and that one's debated. They're arguing over the validity of that data, but it has been brought up as a possibility. Phosphine just doesn't hang around long in nature. So if it's out there, the only way we know of that it can get generated is actually a process of life. That's the case on Earth. Now, that doesn't mean that we just haven't imagined all the possible chemical pathways yet. So all that kind of reasoning is always kind of based on what we know so far. You have to accept that, okay, at least based on what we know, it's possible. Now, they still haven't decided for sure if there is phosphine on Venus or not, and they haven't really come up with any other mechanism for generating it. So that one's still being debated. So what are the challenges then? If you're going to do this kind of stuff, I've already hinted at what the problems are. One is non-biological processes, maybe a way that we just never thought of it before. And there's things like volcanoes. They spew up all kinds of stuff into the atmosphere, and after it settles down, whatever chemicals they threw up is kind of unnatural. It gets reacted away and it's gone. Solar energy. If you have water vapor up in the upper atmosphere, the sun's going to interact with that. Some of that will dissociate into hydrogen and oxygen. And so that could produce oxygen. And that's kind of a small scale kind of a thing, but those are the kind of things you have to worry about. And then, of course, just purely unknown processes. The other thing is that there is a lot of noise. Now, Doug, you mentioned the turbulence and so on that comes with red dwarfs. That basically generates just a whole lot of noise in general. It makes it hard to tell what's going on. And the other thing is, if there are a lot of chemicals, we look at spectra, which we'll talk about in a minute, and it just gets confusing because there can be so many ways of generating some of the same spectra. What's an example of doing this? It all comes down to the term spectroscopy. What you're looking at are frequencies. In the case of absorption spectroscopy, which is the main one we're looking at right now, it's kind of illustrated in this picture where you got some distant sun, that's the white orb there. You got a planet going in front of it. It's in transit. That's where the word transit comes in. And by the way, of course, we detect those planets by noticing periodic dimness as that planet crosses the surface. But then the next thing is, what is the spectrum? So if you imagine, look at this diagram here where you're plotting the wavelength, basically the color. You can think of the frequency or the color of the light. It's plotted on the horizontal axis here. And how intense is that light? Well, if you're not looking at the planet itself, the star itself has some spectrum. And just imagine for a minute that it's pretty flat across the whole region, meaning pretty much all colors almost equally, which is kind of what's assumed in this picture. Now, the thing is, when it passes through the atmosphere, which means on the edge of that planetary surface, some of that's going to get absorbed, and different chemicals that are in the atmosphere will absorb it and certainly cause dips in that frequency response. So that you're seeing in this curve here, if you get a dip, and you can associate that with different chemicals like carbon dioxide and this and that. And these things, of course, can be proven in Earth-based labs, so you don't have to speculate. I mean, you simply set up that gas, you see how light goes through it, and you have your information. So that's what they're looking at. Now, there's similar processes for looking at reflections off of surfaces, like water or something, and emission, where you simply look at what's actually emitted. That's more typically going to be in the infrared region. If there's heat radiating off of a planet, sometimes there's going to be spikes in one area or another, which could indicate different chemicals. So what about this K2-18b? Well, the Hubble telescope did some initial studies back in 2016 through 2019, and they're pretty sure they found water vapor, hydrogen, and helium. But they couldn't do better than that until the James Webb Space Telescope came along. And they concluded that there were some carbon-bearing molecules, and that included methane and CO2, and the dimethyl sulfide, and actually a closely related compound. On Earth, anyway, the only way we know that that gets produced is by marine life, like phytoplankton. Now, the thing is, there's like 1,000 times more of this stuff than there is on Earth, so that's an interesting data point. But anyway, they said there's possibility. Now, this is still in dispute. What they would say is it's not really confirmed in the sense that a lot of people are still arguing over the data. Did they interpret it right? This happens all the time. This is how science progresses. You test and retest, and people try to reproduce everything, and sooner or later they'll come to better conclusions. But at least there's good reason to believe there's something going on here. It may be the strongest evidence we've had of some kind of life beyond Earth so far.
One more?
Yeah.
My understanding is that the dimethyl sulfide has a distinct odor on Earth. Did you run across that mentioned?
Almost every sulfur compound that does.
Yeah.
I don't know specifically that one.
Boiled cabbage. That hypothetically this planet might smell like boiled cabbage.
Let's
if
go
you were there.
Yeah.
There you go.
Sounds good. Yeah. All right. So anyway, there's more and more exoplanets being discovered all the time, mainly because we have more sensitive telescopes now than we did before. And in particular, that transit kind of methodology where you look for the periodic dimming of a star because the planet transits in front of it is picking up a lot of that. They found 5,900 roughly. That was as of this week anyway. I had run this like a week ago, and the number was smaller, so they're constantly coming up with new ones. They've broken it up by the ways they discovered it. It doesn't matter that much, but it really comes down to, you can see that there's just a constantly increasing amount here. There was a big jump around 2016, which was due to the Hubble Space Telescope, which actually is not in operation anymore. That really kicked things off, and then, of course, the James Webb Space Telescope came along. So there's just a whole lot of these being discovered. And what they're trying to do is look at every one of these. When they get a chance, they're trying to look at the atmospheres or any other evidence they have as to what's going on. Okay, next question then is, what about the intelligent life case? What are the challenges? Well, first of all, those aliens might not want to be found. I think anybody who's read much science fiction has imagined, well, there's a lot of them out there. Evolution gives you conflicting ideas. One says everything competes and tries to wipe out everything else. The other says, well, sometimes it helps different groups to work together in a synergy kind of a case. So who knows? There's always that possibility they don't want to be found. The dark forest theory that actually all the intelligent civilizations are really afraid there might be people out there that are superior to them and they don't want to get found because they'll get wiped out. Our past experience on Earth with native tribes that come into contact with advanced civilizations, they don't tend to do very well. We don't want to be those guys. So, maybe you just hold off. There's other challenges, though, and that's, well, one is just detecting that there's any kind of radio transmissions at all on the assumption that they're transmitting it on purpose or even just by accident, just because they're communicating. We don't know how they modulate their signals. On Earth, there's AM, where on a radio frequency you superimpose the audio signal pretty directly, FM, where you vary the frequency. That kind of stuff, you probably could recognize that, but things are getting more complicated. Since World War II, the spread spectrum kind of things, kind of the whole idea is spread out over a lot of frequencies. And that basically makes it harder and harder to even recognize if you're dealing, and if you're even seeing anything that has anything to do with intelligence. You might say, in a way, especially when you start introducing encryption, the goal of that is to basically generate signals that are indistinguishable from noise. If you do that, you have succeeded completely in your encryption. And unfortunately, probably any aliens that are out there have probably been doing this longer than we have. If they choose to hide themselves, they probably could do it pretty well. But anyway, so there have been several notable organizations associated with trying to see, are there other civilizations out there, by listening with radio telescopes, as shown by the one here. There is SETI, the original organization. There's a SETI Institute, Search for Extraterrestrial Intelligence. They really haven't found anything. Now, they have a couple of what you might call anomalies, where they cannot explain something, but the problem is it's never been repeated. And I think they've had maybe just a couple of these, one called the wow signal, and there was some other one. But if you can't really ever repeat it, it makes it dubious that it was just some kind of a fluke or what. Now, where do they look? I mean, how do you decide what to listen to? Actually, the galaxy kind of forces a lot of it on us. There's just too much noise at lower frequencies below the microwave range, and that's kind of shown on this graph here on the left-hand side. And on the right-hand side, you start getting a lot of interference as well, especially if you're in an atmosphere like Earth. There's just so much stuff, water and hydrogen and everything, and oxygen, that absorbs a lot of this stuff. And it basically interferes. This is a plot of noise as a function of frequency. And if you were outside of Earth, it turns out there's still a lot of noise out there. It's kind of a nice, almost like a Goldilocks zone kind of a phenomenon between maybe 1 to 10 gigahertz frequencies, where there's a good chance that something transmitted could go a long, long way and still get noticed. So they're focusing on that. Any of these studies do that. You're kind of forced to being on Earth, but even if you were to set up something in space, you would probably still focus on these frequencies more than the others. How do you think about this? Well, people have worked with audio signals and may be familiar with spectrograms, and they kind of think the same way. What's a spectrogram? Well, what are you looking for? You're looking for certain frequencies, and you're looking for things like spikes that happen over time. So you're looking at things based on time, and you're looking for things based on frequency. So they put it together in one diagram. This actually is a voice print of somebody saying some word. You have the horizontal axis here is time. So it says going from 0 to 1 second here. They show you what frequencies are happening. It's really a 3D plot. You could imagine just doing a 3D plot of this, citing the intensity, but they do it with color for the third dimension. They indicate this on the right-hand side. The brightest signal is the loudest, if you will. The yellow here is the bright. So, for instance, imagine if you were just doing a spectrogram of, say, somebody playing the piano. Suppose they hit a single note. There's maybe one frequency right there. Maybe you hit a note. And then maybe at the same time, you hit a higher note. So the frequency is going up as you go up that diagram. So in that case, I would say that maybe you're hitting like 3 notes at once. And that's dominant. Now, there's a lot of other just noise in there, and that tends to be a lot of the rest of the stuff that's there. But the key message is in that. And then, for instance, maybe it gets quiet. Maybe, like, for instance, if a person is talking, they say something, there's a pause between the words, then there's just not much there at all. And then it starts up again, maybe at a different set of frequencies and so on. So that's what they're looking at. You're basically looking at a combination of time, and you're looking for things like sequences there. If somebody is talking or sending some kind of a signal, it'll have a definite sequence, but they might involve different frequencies. And so that's just the way they think about it. You're probably not going to decode actual words. Who knows what the aliens are saying? But you're just really looking for the existence of some kind of communication. And that's really about the best they can do. Now, there is another project called Breakthrough Listen. It's sort of the newer version of the SETI. This was founded back in 2016. Basically, one guy provided the money. He was an entrepreneur and had a lot of money, so he put up $100 million to fund this study. It's over a 10-year period, so it's almost over. This is headquartered at the University of Oxford. It had some big names associated with it. Stephen Hawking is a co-founder of this particular group. And on their board, they had people like Frank Drake, the guy who came up with the Drake equation, which is saying, well, it's hard to estimate what are the probabilities of life existing out there. So instead, you break it up into a whole bunch of smaller probabilities and multiply them all together, where each of the smaller ones are also impossible to figure out. But at least it was an attempt to formalize things. I mean, at least the first parts of it, we know now that there are a lot of other stars that have planets around them that maybe have habitable zones, and you just keep applying probabilities for each of those things. So anyway, a lot of those kind of people got involved in this. It's been funded pretty well. And so what are they looking at? Well, they want to look at all stars within 16 light years. There's only about 43 of those. But you figure, okay, let's look at the close ones. So that's an obvious target. But they're looking at other nearby stars. So what they do is they just spend time looking at each one and looking at 100 nearby galaxies and known exoplanets. And of course, that increases all the time. So they never quite finish that job. And the other thing they explicitly said was, let's try one of everything. In other words, there's a lot of weird stuff out there because you're trying to not only detect life, really you're looking for other weird phenomena that may indicate some problem with our models of physics. And so, they discovered things like pulsars where they have really strong pulses. They're just saying, try one of everything. Every weird phenomenon that we know, let's look in that area and see what kind of signatures we get and see if we can learn something from that. So what they did was they purchased time on a lot of radio telescopes. Yeah, this question. Okay, so the question is what happens after the end of the 10 years in 2026? Don't know. Very short answer. Don't know on that one. I was reading up on them, and I did not find any information on that. But you have to assume a lot of people are getting paid by this project. Surely they're going to try to go out and raise some more money. So it's like any other research kind of project. You go out and you find funding any way you can. They had it easy. They had it easy the first time. They got a guy that funded it. So anyway, in terms of technically what they're doing, basically they're monitoring every frequency from 1 through 10 gigahertz, again, microwave kind of frequencies. But it's amazing how sensitive they're saying it is. They say they can detect an aircraft radar transmitting to us from any of the 1,000 nearest stars. So that's pretty sensitive. I was impressed with that. I wouldn't have guessed that we could do anything that sensitive. Now, they are also doing some optical laser searches, looking for laser light. This is a smaller part of that project, but they are doing that. And they claim they could detect a 100-watt laser from 4.25 light years away. So now there aren't many stars 4.25 light years away, but still that's a good place to look. There's at least one. The biggest problem, of course, is determining what's natural and what isn't. And actually, if anything, you hope that we learn more about physics from the things that we just discovered that we didn't realize were out there. One thing about the natural versus artificial signals, though, is that most natural phenomena are pretty broadband, meaning they affect a lot of frequencies. And as an example of that, for instance, clouds of hydroxyl ions, I think, is something that happens a lot out in space. That's associated with very, very specific frequencies. However, all those clouds are moving. And so they're moving, and some of them might be moving pretty fast. So some of those things, there's Doppler shift that's going to go on, where basically what you see as the frequency depends on how it's moving relative to you. And some of them are moving toward you, some are moving away from you. So it tends to spread out the frequency. You're not really going to get one narrow little frequency. It tends to get spread out much wider. So they're looking for a narrow band, very, very narrow band, which is more like what we would do, unless we're trying to hide ourselves with spread spectrum kind of techniques or something. So they're looking for that, or just short bursts that are wider range of frequencies. That'll pick up some of the stuff that we would do. Now, the other thing is they're automatically detecting these events. So they're using clustering techniques. They call it AI, but it really comes down to fairly standard pattern recognition kind of stuff. But the main thing is, given those combinations, various patterns of frequencies and time, they're going to try to group them together, and then they themselves will label them as, oh, that's a pulsar, or that's something else. And then the ones that don't fall in any normal group, they're going to get the special attention. The other thing is that data is being made available to the public. They're apparently cooperating a little bit with the original SETI group, and at Berkeley or somewhere, they're setting up some data access. So anyway, that's the end of the story on that one.
Other space-related videos or slide presentations by me are available at the link shown here. That includes a list of videos at my YouTube channel, so you can view them or subscribe for notifications about future videos. These presentations are mostly made as part of the meetings of National Space Society's North Houston chapter, and the link to that is shown. Topics like these are presented as part of a monthly news segment, and there are also lots of other interesting speakers and open discussions. You can attend in person or online via Zoom. Come join us.